So to kind of unpack this for you, he came up with these 4 equations of motion. But I'm going to show you that these 4 equations actually can be derived from the basic definitions of motion and actually using a little bit of common sense. So here's what we're going to do. We're going to think about what if, a little thought experiment. What if one day Galileo decides to go skiing in the Italian Alps here? There we go. So here's Galileo, and I'm pretty sure he didn't really go skiing. This is just a good story here. So please don't go home and tell your parents that we learned about how Galileo went skiing. It's not historical. It's just a way to look at it. And he's skiing down this hill. And just to make life easier here, I'm going to pick a nice, easy number. I'm going to say that he's accelerating down the hill under the influence of gravity at a rate of -2 meters per second squared. And if the hill stays constant, does acceleration change, or is it going to stay constant? What do you think? It's going to stay constant. And here's what we're going to do. We're going to look at what would happen theoretically for the first, quote-unquote, 5 seconds of constant acceleration, free fall, if you will, pulling you down this hill. And there's this pattern. It doesn't matter what kind of hill you pick, you're always going to get this pattern. And that's what Galileo discovered. It's a fingerprint of gravity. So here's what we're going to try to figure out. We're going to try to figure out this thing called VF. You know what VF stands for? That's your velocity what? Final. That's your speed at the end of accelerating down the hill. At the very start, let's just make everything 0. You're not moving. Your V average, that's your average velocity. And then what's delta x a fancy word for? That's your change in your position, your displacement. It's kind of like distance, but with direction. So everything's 0 at the very start. So here we go. After 1 second, if your acceleration down this mountain is -2 meters per second every second, after 1 second, how fast would you speed up to if you're skiing down this hill? You would speed up to negative what? If it's 2 meters per second every second, it would be -2, right? And why negative? Negative just means we're going which way? We're going down. And in fact, that's usually a sign convention we're going to use to keep things consistent. We're going to call going up positive, going down negative. How about to the right? Let's call to the right what? Positive, and to the left, negative. So in this case, we're just looking at it in terms of going down the hill. That's our frame of reference. How about after 2 seconds? Do you see the pattern? If you speed up by 2 meters per second every second, after 2 seconds, you can speed up to what? You guys okay here? Every second we can speed up by what? By 2. It's going to speed up to what? -4. Let me zoom in if that's a little bit easier to see. How about after 3 seconds? What do you think? -6. You guys are awesome. How about after 4 seconds? 8. How about after 5 seconds? 10. That's what acceleration means. It's a rate of change of a rate of change. Next, we're going to look at the average velocity. This is commonly confused with the instantaneous initial or final velocity. Why is this important? We'll see in a second. So how do you find the average velocity? It's pretty simple. The average velocity is just the sum of your initial plus your final velocity divided by 2. If I started off at 0 and I ended up at -2, I'm going to do this in green. What's the average of 0 and -2? Average of 0 and 2 is what? 1, right? You started off at 0, you sped up to 2. By the way, what I'm doing is I'm actually tricking you into using 3 out of our 4 new equations. You're just not realizing it. I'll show you in a second. After 2 seconds, what would your average velocity be? You started off at 0, you ended up at -4. So what's the average of 0 and -4? It'd be what? -2. So in fact, the average velocity is just half your final velocity, isn't it? What's the average of 0 and -6? -3. How about what would be next? -4 and negative what? 5. So I picked an easy number for acceleration to give us easy numbers as we think about acceleration here. So now, here's the kicker. Here's the tricky part. This is where the metal meets the pedal. This is to see if you can really put together the physics of how constant acceleration motion works. Next, we want to find, it's one thing to say how long, that's time. It's another thing to say how fast at the end of speeding up, that's your velocity final. It's another thing to say how fast on average. It's another thing to say how fast you change how fast you're going, that's acceleration. The last question is how far. Usually that's all someone wants to know. So if you are skiing down a hill and you accelerate at the rate of -2 meters per second every second, after 1 second, how far will you ski down that hill? Common mistake is to say that, well, you speed up to -2 meters per second. For 1 second, you're going to go 2 meters. That's actually incorrect because you start off going 0, you speed up to -2. So you're not moving -2 meters per second until the end of 2 seconds. You see that? So if he started off at 0 and he sped up to -2, on average, he was only going how fast? Only -1 meter per second for 1 second. Therefore, he will go down the hill 1 meter in the first second. You see that? How about after 2 seconds? After 2 seconds, he sped up to -4. So did he go 8 meters down the hill? On average, you're only going how fast? Negative what? 2 meters per second for 2 seconds. So how far? 4 meters. You see that? So in other words, to get the final distance down the hill, all you got to do is take the time times the average speed. So how about after 3 seconds? You're going to go what? How far down the hill? 3 times 3 is 9 meters. How about after 4 seconds? 16. How about after 5 seconds? How far, guys? 25. Hey, wait a second. Is there a pattern there? 1, 4, 9, 16, 25. What are you guys seeing there? What would be next? 36, 49. What Galileo discovered is a distance you fall under a constant acceleration is proportional to the square of time. You get an exponential relationship there because you are constantly accelerating. This doesn't seem like that was difficult to discover, but for like 3,000 to 4,000 years of human history, nobody got it. So we got to give props to Galileo for putting this all together.